Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should keep you up at night, but probably won't. Right now, as you're listening to this, roughly 100 billion neutrinos from the sun just passed through your body. In the time it takes you to blink, another 100 billion will follow. They're travelling at nearly the speed of light and they don't even notice you're there. Your entire body, skin, bones, organs, all of it, is essentially invisible to them, offering no more resistance than empty space. By the time you finish listening to this, about 10 quadrillion solar neutrinos will have passed through you, and you won't have felt a single one. And here's the thing that blows my mind. This isn't some exotic phenomenon happening in a particle accelerator. This is just Tuesday. This is reality, happening constantly, everywhere, to everyone, completely unnoticed. This relentless, silent rain of particles is a tiny, almost imperceptible echo of the universe's grandest story, its beginning. Because at its heart, the question of how did the universe begin isn't just about a moment in time, but about the very fabric of existence, the forces, the particles, the laws that govern everything from these fleeting neutrinos to the majestic swirl of a galaxy. It's about how complexity arose from simplicity, how structure emerged from chaos, and how the vast, intricate cosmos we inhabit burst forth from a state almost beyond imagination. This isn't just a historical account. It's an exploration of the fundamental nature of reality itself, a journey to the edge of what we can know, where the universe was once so small, so hot and so dense that the very concepts of space and time, as we understand them, bend and break. It's a story of ultimate transformation, a cosmic awakening that continues to unfold even through the silent passage of neutrinos through your very being. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's try to picture the impossible. Imagine a space so utterly devoid of anything that even the concept of empty seems too generous. No stars, no planets, no light, no dark. Just nothing. But here's the mind-bending part. The story of our universe doesn't begin in this kind of nothing. It begins with something far stranger. Something that challenges our very definition of existence. A state where all the matter, all the energy, all of space and time that makes up everything we see was compressed into a region smaller than a single atom. Not just a region in space, but a region that was space itself. This isn't just a difficult concept. It's where our everyday intuition about size, time, and even reality completely breaks down. This is where physics gets genuinely strange, and where the universe's grand narrative truly begins. The prevailing scientific model for the origin of our universe is often called the unquote one. But that name, coined by astronomer Fred Hoyle in a somewhat derisive manner, is actually a bit misleading. It conjures images of an explosion, like a firecracker going off in a pre-existing dark void. That's not what happened. The Big Bang wasn't an explosion in space. It was an explosion of space. Imagine a tiny, infinitely dense point, a singularity, that contained all the energy, all the matter, and all the information that would ever become our universe. Then this singularity didn't explode outward into something else. Rather, space itself began to expand from this point, carrying everything within it along for the ride. There was no outside for it to expand into, because the universe is everything. This fundamental distinction is crucial to grasping the true nature of our cosmic beginnings. How do we even begin to understand something so utterly beyond our direct experience? We don't have a time machine. We can't rewind the clock 13.8 billion years to witness the moment of creation. Instead, we rely on the universe itself as our ultimate laboratory. The evidence for the Big Bang isn't a single smoking gun, but a convergence of multiple independent lines of observation, each pointing to the same conclusion. One of the earliest and most compelling pieces of evidence came from Edwin Hubble in the late 1920s. He observed that distant galaxies aren't just moving, they're moving away from us, and the farther away they are, the faster they're receding. This isn't because we're at the center of the universe. It's because space itself is expanding, stretching the light waves from these galaxies as they travel, shifting them towards the red end of the spectrum, a phenomenon known as cosmological redshift. If everything is expanding outward, then logically, if we run the cosmic movie in reverse, everything must have been closer together in the past, and if we rewind far enough, everything converges to that single, unimaginably dense point. Another cornerstone of the Big Bang model is the cosmic microwave background, or CMB. This isn't just a fancy name, it's literally the afterglow of the Big Bang. Imagine the early universe as an incredibly hot, dense fog of plasma, so opaque that light couldn't travel freely through it. Photons were constantly scattering off free electrons and protons, like trying to walk through a thick crowd. But as the universe expanded and cooled over about 380,000 years, it reached a critical temperature, around 3000 Kelvin. At this point, electrons and protons could finally combine to form stable, neutral hydrogen atoms. This event, known as recombination, suddenly made the universe transparent. The photons that had been trapped for hundreds of thousands of years were finally free to stream across the cosmos. Today, after 13.8 billion years of expansion, those photons have been stretched and cooled to a mere 2.7 Kelvin, appearing as faint microwave radiation coming from every direction in space. It's the oldest light in the universe, a direct snapshot of the cosmos when it was just a baby, and its uniform presence and precise temperature are powerful confirmations of the Big Bang. So, let's dive into the very first moments, the infinitesimal ignition. We're talking about timescales so fleeting they defy human comprehension. The first 10 hour 43 seconds after the Big Bang is known as the Planck epoch. During this period, the universe was so incredibly hot and dense, temperatures exceeding 10^32 Kelvin, densities beyond 10 or 96 kilograms per cubic meter, that all four fundamental forces of nature, which we experience separately today, are thought to have been unified into a single gun. Quote 3. We're talking about gravity, the strong nuclear force, the weak nuclear force, and electromagnetism, all indistinguishable, operating as one. Our current laws of physics, particularly general relativity and quantum mechanics, break down when trying to describe this epoch. This is the realm where quantum gravity theories like string theory or loop quantum gravity attempt to provide answers, but currently we don't have a complete experimentally verified theory that can fully describe the universe at this extreme scale. It's a theoretical frontier, a deep mystery at the very heart of creation. As the universe expanded and cooled ever so slightly, the first of these unified forces began to freeze out or separate from the others. This happened at around 10 to 36 seconds. Which force split off first? Gravity. This is where the universe started to behave a little more predictably, at least in theory. The remaining three forces, the strong, weak, and electromagnetic forces, were still unified into what physicists call a grand unified theory, or gut force. But even this unified gut force wouldn't last long. As the temperature continued to drop, the strong nuclear force, which binds quarks together to form protons and neutrons, separated from the electro-weak force, the unified weak and electromagnetic forces. This separation, occurring around 10 and 12 seconds after the Big Bang, released an enormous amount of energy, thought to be the driving force behind a phenomenon called cosmic inflation. Cosmic inflation is a truly mind-bending concept, a period of extraordinarily rapid exponential expansion that occurred between roughly 10^36 and 10^32 seconds after the Big Bang. During this unimaginably brief interval, the universe expanded by a factor of at least 10^26, possibly much more. To put that in perspective, imagine a single atom suddenly swelling to the size of an entire galaxy in a fraction of a blink. This isn't just a theoretical contrivance. Inflation elegantly solves several puzzles that the standard Big Bang model initially struggled with. For instance, it explains why the universe appears so remarkably flat and uniform on large scales, like smoothing out wrinkles on a balloon by inflating it to an enormous size. It also explains the horizon problem, which asks how distant regions of the universe, now separated by billions of light years, could have had time to communicate and reach the same temperature, as evidenced by the uniform CMB. Inflation suggests they were once much closer together, allowing thermal equilibrium to be established before the rapid expansion pushed them apart. After inflation ended, the universe was a superheated, dense soup of fundamental particles, primarily quarks, gluons, and leptons, like electrons and neutrinos, along with their antimatter counterparts. This was a quark-gluon plasma, a state of matter so hot, trillions of degrees Celsius, that quarks couldn't bind together to form protons and neutrons. Instead, they moved freely, constantly colliding and interacting. In this incredibly energetic environment, matter and antimatter were being created and annihilated in a continuous dance, following Einstein's famous equation E = mc2. Energy would spontaneously convert into particle-antiparticle pairs, like an electron and a positron, and then these pairs would almost immediately collide and convert back into pure energy. It was a perfect, symmetrical ballet of creation and destruction, but here's where the universe took a crucial, almost miraculous turn. For our universe to exist as we know it, with all its stars, galaxies, and life, there had to be a slight imbalance in that symmetrical dance. For every billion antiquarks, there were 1,000,000,001 quarks. For every billion antileptons, 1,000,000,001 leptons. This tiny, almost imperceptible asymmetry, known as baryogenesis, is one of the most profound mysteries in cosmology. We don't fully understand its precise mechanism, but we know it happened. As the universe continued to cool, the average energy of the photons dropped below the energy required to create new particle-antiparticle pairs. The existing pairs annihilated each other, converting back into photons, but because of that minuscule excess, a tiny residue of matter, about one particle for every billion photons was left over. This leftover matter, this cosmic residue, is what eventually formed all the protons, neutrons, electrons, and ultimately everything we see around us today. Without this exquisite, almost unbelievable imbalance, the universe would be nothing more than a vast sea of photons, eternally dark and lifeless. The sheer energy density of this early universe, the incredibly rapid expansion, and the precise conditions that allowed for the triumph of matter over antimatter, all point to a beginning that was anything but placid. It was a furnace of creation, a perfect particle accelerator operating on a cosmic scale, forging the very building blocks of existence from pure energy. The universe, in its infancy, was a place of extremes, where the laws of physics were pushed to their limits, and where the slightest deviation in fundamental constants could have led to a completely different and likely sterile outcome. So, we've journeyed through the first tiny fraction of a second, from an unimaginable singularity through a period of explosive inflation to a dense hot plasma where matter barely outlasted its antimatter twin. We've seen how gravity separated, how the strong nuclear force emerged, and how the fundamental particles of the universe began their existence in a cosmic dance of creation and annihilation. This incredibly brief, yet profoundly impactful, epoch set the stage for everything that would follow. The universe was still too hot for even protons and neutrons to form stable structures, but the raw ingredients were there, swirling in a superheated soup. The next question naturally arises: what happened as this chaotic, energetic plasma continued to cool? How did these fundamental particles begin to assemble into the more complex structures that would eventually populate the cosmos? That question leads us directly to the next crucial stage, the formation of the first stable building blocks of atomic nuclei, a process known as Big Bang nucleosynthesis, which we'll explore in our next chapter. All right, welcome back to Quote, Isti, where we're continuing our incredible journey into the ultimate origin story. How our universe, this vast, intricate tapestry of stars and galaxies, came to be. Last time, we left off with a mind-bending mystery, didn't we? The universe, barely a fraction of a second old, had just undergone baryogenesis, a process that left behind a cosmic residue, a tiny, almost imperceptible excess of matter over antimatter. For every billion antimatter particles, there was just one extra matter particle. A cosmic rounding error, perhaps, but one that allowed anything to exist beyond a fleeting flash of annihilation. And here's where the story gets even more fascinating, because with that matter surplus, our universe was finally ready to start building. Imagine, if you can, the universe at a mere millionth of a second old. The temperature has cooled, but it's still an inferno, around 1 trillion degrees Kelvin. Before this point, quarks, the fundamental building blocks of matter, were free-spirited, zipping around independently in a superheated dense plasma. But as the universe continued its rapid expansion and cooling, a critical threshold was crossed. This strong nuclear force, one of the 4 fundamental forces we talked about, finally asserted its dominance, acting like an invisible cosmic glue. This is where quarks, those tiny ephemeral particles, began to find their partners. 3 quarks bound tightly together by gluons, formed into stable packets we call sunhadrons. The most familiar of these, and certainly the most important for our story, are protons and just neutrons. Think of it. From a swirling, chaotic soup of fundamental particles, the very first, most basic building blocks of atomic nuclei were forged. It's like the universe finally had enough sense to assemble its initial Lego bricks, preparing for something much grander. As these protons and neutrons were coming together, another subtle but profound event was unfolding, around 1 second after the Big Bang. The universe was still a hot, dense environment, but it was cooling rapidly. At this stage, electrons and their antimatter counterparts, positrons, were still being created and annihilated in a lively cosmic dance. But the neutrinos, those ghostly particles we mentioned right at the top of our first episode, the ones passing through your body unnoticed right now, they were doing something significant. Up until this point, neutrinos were actively interacting with other particles in the hot, dense plasma. They were part of the cosmic conversation, so to speak. But as the universe expanded and cooled, the density dropped, and these interactions became less and less frequent. Around the 1 second mark, neutrinos effectively decoupled from the rest of the cosmic soup. They stopped interacting significantly with other matter and energy. This event left behind a cosmic relic, much like the cosmic microwave background we discussed. It's called the cosmic neutrino background, or CNB. It's a faint sea of neutrinos, travelling freely through space since the universe was just a second old. Detecting it is incredibly difficult, even harder than the CMB, because neutrinos interact so weakly. But its theoretical existence is another powerful piece of evidence supporting our understanding of the early universe. It's the universe's way of saying, I was here and this is what I was doing, and it blows my mind to think that those same types of particles, those silent, fleeting travellers, are still ghosting through us every single moment. Now, with our protons and neutrons formed, and the neutrinos off on their solo journeys, the stage was set for one of the most crucial acts in the universe's early drama. Big Bang nucleosynthesis, or BBN. This is where the universe literally became a cosmic alchemist, forging the first atomic nuclei. Picture this: the clock is ticking from roughly 3 minutes to about 20 minutes after the Big Bang. The temperature has dropped further, now to a blistering but manageable 1,000,000,000 degrees Kelvin. At these temperatures, protons and neutrons are still zipping around furiously, but they're finally cool enough to stick together without being immediately ripped apart. The key player here is deuterium, an isotope of hydrogen consisting of 1 proton and 1 neutron. It's the crucial intermediate step. At higher temperatures, any deuterium that formed would be instantly shattered by high-energy photons. This is known as the deuterium bottleneck. But once the universe cooled sufficiently, deuterium could form and survive, and once deuterium was stable, the floodgates opened. Protons and neutrons rapidly fused to form a light element smorgasbord. Deuterium, 1 proton, 1 neutron. Helium-3, 2 protons, 1 neutron. And most importantly, helium-SUTS, 2 protons, 2 neutrons, which is incredibly stable. A tiny, tiny amount of lithium-7 was also created, but the process essentially stopped there. Why? Because by the time heavier elements like carbon or oxygen could start forming, the universe had expanded and cooled too much. The density and temperature were no longer sufficient to sustain the nuclear fusion reactions needed for heavier nuclei. It was a brief, intense burst of cosmic creation, a 20-minute window of opportunity. The result of this 20-minute cosmic pressure cooker a universe composed of approximately the 75% hydrogen gas and the 25% helium-4. By mass, with trace amounts of deuterium, helium-3 and lithium. This predicted elemental abundance is one of the most stunning triumphs of the Big Bang model. When astronomers observe the oldest, most pristine gas clouds in the universe today, they find precisely these proportions. It's like finding the original recipe card for the universe, perfectly preserved centuries later. This isn't just theory, it's a cosmic fingerprint, undeniable proof of the universe's fiery childhood. The lifting veil, recombination, and the cosmic microwave background. Now, fast forward past the 20-minute mark. The fusion has stopped, and the universe is filled with a hot, expanding plasma of hydrogen nuclei, protons, helium nuclei, and free-floating electrons. For hundreds of thousands of years, the universe exists in this state, often referred to as the quote, twelve. Not because there was no light, but because it was an opaque, foggy place. Imagine trying to see through a dense fog. The light particles, photons, are constantly bumping into and scattering off the free electrons. They can't travel far without hitting something, so the universe is effectively opaque, a brilliant, blinding, but utterly impenetrable glow. But the universe continues to expand, and with expansion comes cooling. Around 380,000 years after the Big Bang, the temperature drops to about 3,000 Kelvin, roughly 2,700 degrees Celsius or 4,900 degrees Fahrenheit. This is the magic number. At this temperature, the free electrons finally slow down enough to be captured by the hydrogen and helium nuclei. They combine to form your neutral atoms of hydrogen and helium. This event is called recombination, though it's a bit of a misnomer, as atoms were combining for the first time, not combining. And here's the truly pivotal moment. When the electrons are no longer free, the photons are no longer scattered. They are suddenly free to travel unimpeded across the vast expanse of the cosmos. This is the moment the universe became, transparent. The quote 13 lifted, and those photons released from their atomic prisons are the very light we detect today as the cosmic microwave background, CMB. It's literally the Ankaustipelsendan of the universe, a fossilized echo from when the cosmos was just a baby, a mere 380,000 years old. When we look at the CMB, we're not just seeing light, we're seeing a snapshot. It's the universe's baby picture, showing us a remarkably smooth, uniform distribution of matter and energy. But crucially, it also shows tiny, tiny temperature fluctuations, variations of just a few parts in 100,000. These aren't just random static. These are the unseeds of structure. They are the subtle density variations that gravity would later amplify, the very first whispers of future galaxies and stars. So, the universe has become transparent, filled with neutral hydrogen and helium gas, and significantly, a vast amount of dark matter. We still don't fully understand dark matter, but we know it interacts only through gravity and the weak nuclear force, making it incredibly elusive. However, its gravitational influence is profound. After the CMB, the universe entered another long period of darkness, sometimes called the true. Quote, 15. There were no stars, no galaxies, just a diffuse neutral gas permeated by invisible dark matter. But those tiny density fluctuations in the CMB were slowly, inexorably beginning their work. Gravity, the great cosmic sculptor, began to pull matter together. Dark matter, being immune to electromagnetic forces and pressure, could clump together much more easily than ordinary matter. It started forming invisible gravitational wells, or halos. Over hundreds of millions of years, the ordinary baryonic matter, our hydrogen and helium gas, slowly began to fall into these dark matter halos, drawn in by their immense gravitational pull. As these gas clouds grew denser and denser, the pressure and temperature at their cores began to rise, and then, finally, around 100 to 200 million years after the Big Bang, the pressure and temperature in the densest regions became so extreme that nuclear fusion ignited. The first stars were born. These weren't stars like our Sun. These were the legendary Population 3 stars. Massive, short-lived behemoths composed almost entirely of hydrogen and helium. They were incredibly luminous, burning through their fuel at a furious rate. Their intense ultraviolet radiation began to ionize the surrounding neutral hydrogen, lifting the last vestiges of the Dark Ages. This process, known as reionization, marked the true cosmic dawn. These first stars, in their brief, brilliant lives, also performed another vital cosmic function. They forged the very first heavy elements, carbon, oxygen, iron, through stellar nuclear synthesis. When these massive stars exploded as supernovas, they scattered these newly created elements into the nascent galaxies, enriching the universe and providing the raw materials for future generations of stars, planets, and eventually life itself. From a fleeting, matter-rich soup to the formation of fundamental particles, then the first atomic nuclei, and finally the ignition of the first stars, our universe was undergoing its ultimate transformation. It's a journey from the unimaginably simple to the breathtakingly complex, guided by the fundamental laws of physics. And as we look out at the cosmos today, we see the echoes of these profound moments everywhere, a cosmic story still unfolding, still inspiring, still inviting us to look a little closer and wonder, just how did we get here? Join us next time on Dreamy Science as we continue our cosmic saga, exploring how these first stars and galaxies paved the way for the universe we inhabit today. What questions are bubbling up for you as we traverse this incredible timeline? Let us know in the comments and keep dreaming big. Welcome back to Dreamy Science, where we're unraveling the grandest story ever told, the origin and evolution of our universe. Last time, we peered into the, quote, 19 witnessed the birth of the universe's first gargantuan stars, those short-lived Population 3 pioneers, and marvelled as their cataclysmic supernovae forged the universe's initial heavy elements, reionizing the neutral hydrogen fog and setting the stage for everything that followed. Imagine, if you will, the universe, at this point, a vast expanding canvas, no longer a dense plasma, but a transparent expanse filled with hydrogen and helium gas, dotted with the faint fleeting glow of those first stellar behemoths. The stage is perfectly set, and now gravity, that tireless cosmic sculptor, truly begins its work. We talked about those tiny ripples in the cosmic microwave background, those primordial density fluctuations that were the seeds of everything. Remember how dark matter, that invisible scaffolding, amplified these fluctuations? Well, in the wake of the first stars, as the universe continued its inexorable expansion and cooling, these regions of slightly higher density became gravitational anchors. They started to pull in more and more gas, more and more dark matter, growing steadily, relentlessly. Picture it like this. If the universe were a vast, slowly expanding ocean, these denser regions are like subtle currents, drawing in the surrounding water. Over hundreds of millions of years, these currents strengthened, forming colossal, interconnected structures that we now call the cosmic web. This isn't just a fancy phrase, it's a genuine, mind-bending reality. Observations from powerful telescopes like the Hubble and James Webb Space Telescopes reveal that the universe isn't uniformly distributed. Instead, matter is organized into an intricate, spongy network of filaments, knots, and vast, empty voids. The filaments are like cosmic highways teeming with galaxies, stretching for hundreds of millions of light years. The knots, where multiple filaments intersect, are the most massive structures, home to immense clusters of galaxies, and the voids, they are the desolate, almost galaxy-free expanses between these cosmic threads. And here's the thing that absolutely blows my mind. The existence and structure of this cosmic web are precisely what our simulations, built on the Big Bang model and the properties of dark matter, predict. It's like looking at the universe and seeing the blueprint come to life billions of years later. Within these growing dark matter halos, nestled along the filaments and at the intersections of the cosmic web, vast clouds of gas and dust began to collapse under their own gravity. This is where the magic of galaxy formation truly kicks off. These aren't just isolated stars anymore. These are the first true galactic nurseries. As the gas spirals inward, it heats up, compresses, and forms new generations of stars, not just one or two, but billions upon billions. These early galaxies, forming perhaps 1 billion years or so after the Big Bang, were likely quite different from the majestic spirals and ellipticals we see today. They were probably smaller, more irregular, and frequently collided and merged with each other. This chaotic dance of cosmic collision and merger wasn't destructive, it was formative. Each merger fueled new bursts of star formation, stirred up gas, and contributed to the growth of larger, more complex galaxies. It was a spectacular, violent ballet of creation, driven by gravity and the relentless pull of dark matter. And speaking of violence, many of these early galaxies harboured another incredible phenomenon at their hearts: supermassive black holes. We believe these colossal gravitational beasts grew in tandem with their host galaxies. As gas and dust swirled into their hungry maws, they emitted astonishing amounts of energy across the electromagnetic spectrum, creating what we call quasars, some of the brightest objects in the early universe. These quasars acted like cosmic lighthouses, their brilliant emissions piercing the remaining neutral hydrogen fog, further contributing to the reionization of the universe and, in some cases, even regulating star formation by blowing out gas from their galactic hosts. It's a dynamic, intricate feedback loop that shaped the very architecture of the cosmos. As these galaxies matured, so did the stars within them. The first population 3 stars were gone, having lived fast and died young. But their legacy lived on. The heavy elements they forged, carbon, oxygen, iron, silicon, were now dispersed into the interstellar medium, enriching the gas clouds from which subsequent generations of stars would form. These next generations are what we call population 2 stars. These stars are still relatively metal poor compared to our Sun, but they contain more heavy elements than the pristine population 3 stars. We find these ancient, long-lived population 2 stars today in the halos of galaxies and within globular clusters, spherical collections of hundreds of thousands of stars, tightly bound by gravity, orbiting the galactic centre. These globular clusters are like living fossils, preserving the conditions of the early universe, allowing us to study stars that formed billions of years ago. Then, over eons, as more and more stars lived and died, exploding as supernovae or shedding their outer layers, the interstellar gas became progressively richer in heavy elements. Each generation of stars acted as a cosmic refinery, taking the simple hydrogen and helium, fusing them into heavier elements, and then scattering these elements back into space for the next round of star formation. This continuous cycle of birth, death, and renewal is the very engine of cosmic evolution. From this increasingly enriched gas and dust, a new type of star began to form. Population I stars. These are the stars like our own Sun, rich in metals, meaning they contain a significant proportion of elements heavier than hydrogen and helium. These stars are typically found in the spiral arms of galaxies, within vast clouds of gas and dust, where star formation is still ongoing. Our Sun, a population 1 star, formed about 4.6 billion years ago, a mere youngster in the grand scheme of the universe's 13.8 billion year history. And this brings us to one of the most exciting parts of the story, at least from our perspective, the birth of planets. With the abundance of heavy elements now circulating in the universe, the conditions were finally right for rocky worlds to emerge. Let's try to picture it. A swirling cloud of gas and dust, gravitationally collapsing, begins to flatten into a rotating disk around a newly forming star, a protoplanetary disk. This disk is like a cosmic construction site with the central star acting as the main engine. Within this disk, dust grains, no bigger than specks of glitter, begin to collide and stick together. This process, called accretion, is incredibly slow at first, but inexorable. Over millions of years, these tiny grains coalesce into larger pebbles, then into rocks, then into kilometre-sized chunks called planetesimals. Imagine billions of these planetesimals constantly bumping, grinding, and merging within the disk. As they grow, their gravitational pull increases, allowing them to sweep up even more material. Eventually, some of these planetesimals grow large enough to become protoplanets. Mini-worlds in the making. Closer to the central star, where temperatures are higher, volatile compounds like water, methane, and ammonia are vaporized. This means that the protoplanets forming in the inner regions are primarily made of rock and metal, the ingredients for terrestrial planets, like Earth, Mars, Venus, and Mercury. Further out, beyond what scientists call the frost line, these volatile compounds can condense into ice. Here, the protoplanets have access to much more material, rock, metal, and ice, allowing them to grow much larger and faster. Their immense gravity then enables them to sweep up vast amounts of hydrogen and helium gas from the surrounding disk, forming the gas giants. Like Jupiter and Saturn, beyond them the ice giants Uranus and Neptune form in even colder regions. Our own solar system is a beautiful testament to this process. From the remnants of a supernova that enriched our local corner of the Milky Way with the heavy elements necessary for our existence, a cloud of gas and dust collapsed, formed a protoplanetary disk, and eventually gave rise to the Sun and the 8 planets that orbit it, along with countless asteroids, comets, and moons. It's a story that has played out billions of times across the universe in countless star systems. And this brings us to the ultimate mind-bending culmination of our cosmic journey, the emergence of life. For life to arise, you need a few critical ingredients, the right mix of elements, forged in stars, remember, a stable energy source, a star like our Sun, and the right environmental conditions, like a planet orbiting at just the right distance for liquid water to exist. On our Earth, about 4 billion years ago, in the aftermath of its violent formation, with oceans forming and volcanoes erupting, complex chemistry began to unfold. We don't fully understand the precise steps of abiogenesis, how non-living matter gave rise to the first self-replicating molecules, but we know it happened. And from those humble beginnings, life diversified and evolved over billions of years, adapting, changing, and growing increasingly complex, eventually leading to you, me, and every living thing on this planet. Think about it. The carbon in your body, the oxygen you breathe, the iron in your blood, every single atom heavier than hydrogen and helium was forged in the heart of a star, or in the incredible violence of a supernova explosion, billions of years ago, long before our Sun was even a whisper in the cosmic wind. We are quite literally stardust animated by the universe itself, capable of contemplating its own origins, from an unimaginably hot, dense singularity, through periods of inflation, plasma, and atomic formation, to the first stars, the first galaxies, the first planets, and finally, the first stirrings of life. It's an unbroken chain of cosmic evolution. And this story, while incredibly detailed, is still unfolding. The universe continues to expand, galaxies continue to evolve, stars continue to be born and die, and perhaps, somewhere out there, other forms of life are taking root or already flourishing on worlds we can only dream of. Our journey through the universe's origins has taken us from the infinitesimal to the infinite, from the first fraction of a second to billions of years of cosmic history. We've tackled some of the biggest questions in science, acknowledged the profound mysteries that still remain, dark matter, dark energy, the very beginning of the Big Bang itself, and celebrated the incredible progress humanity has made in understanding our place in this vast, wondrous cosmos. Join us next time on Kestet's Quote 22, as we dive even deeper into some of these lingering enigmas and explore the future of cosmic discovery. Until then, keep looking up and keep wondering. And so, from the crucible of stars, from the delicate dance of elements forged in unimaginable furnaces, we arrive. We, the living, breathing manifestations of stardust, find ourselves on a pale blue dot, orbiting a yellow dwarf star, in a spiral arm of a galaxy we call the Milky Way. It's a journey spanning billions of years, from the infinitesimal flicker of the Planck epoch to the vibrant, complex tapestry of life that pulses around us. We've traced the cosmic story from its earliest whisper to the very moment of our own existence. But here's the thing, the truly mind-bending, awe-inspiring, and sometimes frustrating truth. The story isn't over, not by a long shot. In fact, many of the most profound chapters remain unwritten, or at best are only sketched in the faintest of theoretical ink. We've covered the Quote 23 of the universe's unfolding from the Big Bang to us, but the Quote 24 and the Quote 25 continue to challenge our deepest scientific and philosophical inquiries. Let's take a moment, you and I, to look around us, not just at the immediate world, but at the vast cosmic canvas that continues to evolve. The universe today is a breathtaking spectacle of structure, galaxies, billions upon billions of them, arranged in a colossal, intricate cosmic web. Imagine a vast three-dimensional spiderweb where the threads are filaments of galaxies and galactic clusters, and the empty spaces are immense cosmic voids. This isn't a static painting. It's a dynamic, ever-changing sculpture, a grand cosmic ballet where galaxies collide, merge, and new stars are continuously born from the stellar nurseries nestled within swirling gas clouds. Old stars flare into brilliant supernovae, enriching the cosmic gas with heavier elements, perpetuating the cycle of creation. This is our universe, vibrant and alive, still very much in its prime. But for all the beauty and the intricate physics we've uncovered, a significant portion of this cosmic ballet is performed by invisible dancers, powered by unseen forces. And this brings us back to those profound, lingering mysteries we've touched upon, the ones that keep cosmologists up at night, fueling countless experiments and theoretical frameworks. We're talking, of course, about dark matter and dark energy. Let's start with dark matter, that elusive, ghostly presence that makes up about 27% of the universe's total mass energy content. Remember how we talked about gravity amplifying those tiny density fluctuations in the early universe, eventually leading to the formation of the cosmic web? Well, gravity, as we understand it, just isn't strong enough on its own to have built structures as quickly and as large as we observe them. Something else, some additional gravitational scaffolding, had to be there. And that, my friends, is dark matter. We can't see it. It doesn't interact with light or any other form of electromagnetic radiation. It doesn't absorb, reflect, or emit light. It doesn't seem to interact with ordinary matter through the strong or weak nuclear forces either, except through gravity. It just is. We infer its presence through its gravitational effects. How galaxies spin too fast at their edges without flying apart. How light bends around massive galaxy clusters, a phenomenon called gravitational lensing. And how the cosmic microwave background's subtle temperature variations wouldn't make sense without its influence. It's like trying to weigh an invisible elephant by only observing the compression of the ground beneath its feet. We see the effects, but not the elephant itself. What is dark matter? That's the million-dollar question, possibly the billion-dollar question. Is it made of exotic particles that we haven't yet discovered, like weakly interacting massive particles, or WIMPs? Perhaps incredibly light particles like axions? Or could it be a collection of massive compact halo objects, or machos like rogue planets, or brown dwarfs that just don't emit enough light to be seen? Current evidence leans heavily towards some form of new non-baryonic particle, something fundamentally different from the protons, neutrons and electrons that make up everything we can see and touch. Experiments deep underground and at particle accelerators like the Large Hadron Collider are actively searching for these elusive particles, hoping to catch just one tiny interaction, a single whisper from the dark. Imagine the thrill of that discovery, a whole new fundamental particle, a new window into the very fabric of reality. But if dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine, pushing everything apart. This, to me, is perhaps the most genuinely strange and profound mystery facing us today. Back in the late 1990s, when astronomers were meticulously measuring the expansion rate of the universe, using distant supernovae as cosmic mile markers, they expected to find that the expansion was slowing down due to gravity. Makes sense, right? Gravity pulls things together, so the initial expansion should be decelerating. Instead, they found the opposite. The expansion of the universe is accelerating. It's speeding up. This was a truly revolutionary discovery, earning a Nobel Prize and completely reshaping our understanding of the universe's ultimate fate. It's as if you threw a ball into the air, expecting it to slow down and fall back to Earth, but instead it just kept speeding up, rocketing away into space faster and faster. This mysterious force, this cosmic anti-gravity that pushes space itself apart, is what we call dark energy. It accounts for an astonishing 68% of the universe's total mass energy. Think about that. Everything we can see, everything we've ever touched, smelled, tasted, or heard, stars, planets, galaxies, us, makes up less than 5% of the universe. The rest is this invisible, enigmatic duo, dark matter and dark energy. What is dark energy? Again, we don't know for sure. The simplest explanation, and one that fits current observations remarkably well, is that it's the quote 26. A concept first introduced by Albert Einstein, and later called his Shastassus Quotient 2701, before its modern resurgence. It suggests that dark energy is an intrinsic property of space itself, a constant energy density that doesn't dilute as space expands. As the universe gets bigger, more space means more dark energy, which means even more acceleration. It's a self-perpetuating cosmic push. Other theories propose, quote, 28. A dynamic, evolving energy field, or even modifications to Einstein's theory of gravity itself on cosmic scales. But for now, the cosmological constant remains the leading candidate. A constant, pervasive energy woven into the very fabric of space-time, silently dictating the universe's ultimate destiny. It blows my mind to think that empty space, what we perceive as nothingness, actually contains an inherent energy that is driving the cosmos apart. And what about that ultimate beginning, the Big Bang itself? We've traced the universe back to an unimaginably hot, dense state, a singularity where our current laws of physics break down. But what caused it? What was before it? Was there a, quote 29? These questions push us to the very edge of human comprehension. Some theories venture into the realm of multiverses, suggesting our universe is just one bubble in an infinite sea of universes. Others propose cyclical universes where a, quote 30 might lead to a new, quote 31 dan, a cosmic reincarnation. For now, the Planck epoch, that first tiny fraction of a second, remains a veil, a theoretical frontier where quantum mechanics and general relativity must somehow reconcile. Then there's that tiny, exquisite imbalance of matter over antimatter, that cosmic miracle called baryogenesis. Why did the universe favour matter by just one part in a billion? If it hadn't, if matter and antimatter had annihilated each other completely, the universe would be a desolate sea of photons, without a single atom, without a single star, without us. This slight, unexplained asymmetry is fundamental to our existence. Yet its precise mechanism remains one of the universe's most profound secrets. It's like finding a perfectly balanced scale with a single grain of sand tipping it just so, allowing an entire world to form. How did that grain of sand get there? These are not minor details, my friends. These are the foundational pillars of our cosmic story that are still shrouded in mystery. They remind us that for all our incredible progress, for all the elegant equations and powerful telescopes, we are still very much at the beginning of understanding the universe. And what about the end? What does dark energy's relentless push mean for the universe's ultimate fate? If the acceleration continues, as current evidence suggests, the universe is headed towards what we call the Big Freeze, or heat death. Imagine a future so distant it's almost impossible to grasp. Galaxies will continue to drift away from each other, eventually receding faster than the speed of light from our perspective, leaving our local group of galaxies isolated in a vast, empty cosmic ocean. The light from distant galaxies will stretch to such extreme wavelengths that they become invisible, swallowed by the expanding void. Stars will burn out one by one, their fuel exhausted. Black holes, the ultimate cosmic vacuum cleaners, will eventually evaporate through a process called Hawking radiation, leaving behind only an incredibly thin, cold soup of fundamental particles and photons spread across an ever-expanding, ever-colder space. All structure, all energy gradients, all potential for anything interesting to happen will vanish. The universe will reach a state of maximum entropy, a uniform, featureless expanse of ultimate chill. It's a profoundly lonely and quiet end, an echo of the void from which it all began. But it's billions upon billions of years in the future, a timescale so vast it dwarfs the entire history of our universe to date. For now, we exist in a precious, vibrant window of cosmic time where stars still shine, where galaxies still dance, and where life has found a way to emerge and ponder its own existence. We are the universe's way of looking back at itself, of trying to understand its own magnificent story. The journey of Rayam, quote, 34, is a quest not just for answers, but for the right questions. We marvel at what we know, and we stand in awe before the vastness of what we don't. The universe is a grand, unfolding narrative, and we are privileged to be both its characters and its curious chroniclers. So, as we continue to explore the edges of our knowledge, remember that every mystery is an invitation, every unanswered question, a doorway to new discovery. The cosmos beckons, and our adventure into its profound depths has only just begun. We left off, didn't we? Gazing into the profound abyss of the unknown, standing at the precipice of humanity's greatest questions. We've journeyed from the Plankipuk's unimaginable heat to the universe's predicted cold, empty future, tracing a cosmic narrative woven with wonder and punctuated by startling mysteries. And here's the thing that truly blows my mind. The vast majority of our universe, the very scaffolding upon which galaxies are built and the engine driving its accelerating expansion, remains utterly invisible to us. It's not just out there somewhere, it's everywhere, shaping everything, yet eluding our direct grasp. We're talking, of course, about dark matter and dark energy. These aren't just theoretical placeholders. They are the colossal, silent architects of our cosmic reality, comprising a staggering 95% of the universe's total mass energy content. Think about that for a moment. Everything we can see, touch, measure, and experience, every star, every galaxy, every planet, every living thing, every thought in your head, is merely the luminous, ephemeral foam atop an ocean of unseen forces. It's genuinely strange, isn't it? Like living in a house where 95% of the structure is made of ghost material, yet it holds you up just fine. Let's try to picture this together, because it's a concept that demands our full imaginative power. Imagine a grand cosmic stage. On this stage, the stars perform their brilliant ballets, galaxies swirl in majestic dances, and planets orbit in precise choreography. But beneath the stage, unseen, are the massive, intricate mechanisms, the gears and levers, the hidden hands that move the puppets and orchestrate the entire show. That's dark matter and dark energy. They are the hidden mechanics, the silent directors dictating the universe's grandest performance. The ghostly embrace of dark matter. First, let's peel back the layers on dark matter. We know it's there because we see its gravitational effects. It bends light. It holds galaxies together. It sculpts the cosmic web. Without it, the spinning galaxies we observe would simply fly apart. Their visible matter doesn't provide enough gravity to keep them cohesive. It's like observing a merry-go-round spinning incredibly fast, yet no one is being flung off. You'd conclude there must be some invisible force holding them on, right? That's dark matter for galaxies. Our current understanding tells us that dark matter is not made of the protons, neutrons and electrons that form everything we call, quote, 36p, or, quote, 37 norm matter. It doesn't interact with light. It doesn't absorb, emit or reflect it, which is why it's dark. And it barely interacts with itself or with normal matter, except through gravity. This makes it incredibly elusive. It streams through us constantly, like neutrinos, but with a much greater gravitational tug. Your body, right now, is being permeated by billions of dark matter particles, utterly unnoticed. So if we can't see it, touch it, or directly interact with it, how on earth do we even begin to hunt for it? This is where the ingenuity of human science truly shines. Scientists around the globe are pursuing several fascinating avenues. One leading idea is that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would be massive, as their name suggests, but would interact only through gravity and the weak nuclear force, hence, quote 39. The search for WIMPs involves elaborate underground experiments shielded from cosmic rays, trying to detect the incredibly rare occasions when a WIMP might actually collide with an atomic nucleus in a detector. Think of massive vats of supercooled liquid xenon or germanium crystals, waiting in the absolute quiet of deep mines for that one, almost imperceptible. Quote 40 the faintest echo of a dark matter particle passing through. Experiments like Lux, Xenon, and Super CDMS are precisely this, silent sentinels listening for the universe's most enigmatic whisper. Another prominent candidate for dark matter is the axion, a much lighter particle theorized to solve a different problem in particle physics. The search for axions involves incredibly sensitive detectors designed to convert these elusive particles into photons in the presence of strong magnetic fields. It's like trying to coax a ghost to briefly glow in the dark, just long enough to confirm its existence. Beyond these direct detection efforts, we also look for indirect evidence. If dark matter particles can annihilate with each other, a possibility for some WIMP models, they might produce detectable gamma rays or other particles. Space telescopes like Fermi and ground-based observatories are constantly scanning the cosmos for these potential signatures, particularly from regions expected to be rich in dark matter, like the centers of galaxies or dwarf spheroidal galaxies. And then there's the truly mind-bending possibility. Maybe dark matter isn't a particle at all. Maybe our understanding of gravity itself needs a tweak on cosmic scales. This is where theories of ambient modified Newtonian dynamics, MOND, come into play, suggesting that gravity behaves differently at very low accelerations, negating the need for dark matter. However, MOND struggles to explain observations like the bullet cluster, where two galaxy clusters have collided, separating their visible matter from the gravitational lensing signal which traces dark matter. The bullet cluster is arguably one of the most compelling pieces of evidence for dark matter, showing that the unseen mass has moved independently of the normal glowing gas. It's a cosmic smoking gun, pointing directly to something beyond our visible universe. The accelerating enigma of dark energy. Now, let's turn our attention to the even more mysterious force, dark energy. If dark matter is the unseen scaffolding, dark energy is the invisible engine, accelerating the universe's expansion. Remember, we discovered this acceleration in the late 1990s by observing distant Type Ia supernovae, cosmic lighthouses whose predictable brightness allows us to measure their distance and, crucially, the rate at which the universe is expanding. The shocking discovery was that the expansion isn't slowing down, it's speeding up. This is genuinely counterintuitive. You'd expect gravity, the universe's great unifier, to be pulling everything back together, or at least slowing the outward rush. Instead, it's as if the universe has its foot on the accelerator, and this acceleration implies the existence of a repulsive force, something pushing space apart. That something, that enigmatic push, is what we call dark energy. It accounts for a whopping 68% of the universe's total mass energy density, making it the dominant component of our cosmos. What is dark energy? This is arguably the biggest unsolved puzzle in modern cosmology. The leading candidate is the cosmological constant, first introduced by Albert Einstein, and later called his, quote, 41 none, before its stunning vindication. It proposes that dark energy is an intrinsic property of space itself, the energy of the vacuum. As space expands, more vacuum appears, and thus more dark energy is created, pushing space even further apart. It's a self-perpetuating cosmic engine. The problem with the cosmological constant is its theoretical value. Quantum field theory predicts a vacuum energy density that is many, many orders of magnitude larger than what we observe, a discrepancy of about 120 orders of magnitude, making it, quote, 42. This colossal mismatch tells us that we are fundamentally missing something about the nature of space and energy at its most fundamental level. Other hypotheses include quintessence, a dynamic field whose energy density can change over time, unlike the constant vacuum energy. Or perhaps, like with dark matter, our understanding of gravity needs another revision on the larger scales, leading to theories of a modified gravity that could explain the accelerated expansion without invoking a new energy component. How do we investigate this pervasive invisible force? We rely on large-scale cosmic surveys. We meticulously map the distribution of galaxies across vast stretches of the universe, looking for patterns like baryon acoustic oscillations, BAO, fossilized sound waves from the early universe that act as, quote, 43 to measure distances. By comparing these rulers at different cosmic epochs, we can precisely track the expansion history of the universe and, crucially, how dark energy's influence has changed over time. Projects like the Dark Energy Survey, DES, Euclid, and the Nancy Grace Roman Space Telescope are designed to probe these questions with unprecedented precision, aiming to distinguish between a cosmological constant and more dynamic dark energy models. Beyond comprehension, the before and the why. These are the immediate frontiers of our understanding, the tangible mysteries we are actively chipping away at with incredible experiments and observations. But beyond dark matter and dark energy, we still grapple with the before of the Big Bang and the ultimate why. Our current physics breaks down at the singularity, the initial point of the Big Bang. What happened before? Was there a before? This is where science enters the realm of highly speculative but utterly fascinating theoretical physics. Concepts like quantum gravity, the elusive theory that would unify general relativity with quantum mechanics, are essential here. Theories like string theory and loop quantum gravity attempt to describe the fundamental nature of space and time at the Planck scale, offering potential glimpses into what might have preceded our universe. Could our universe be just one bubble in a vast, infinite multiverse, where other universes with different physical laws constantly pop into existence? Could the Big Bang itself be a rebound from a previous big crunch in a cyclical universe? These aren't questions we can answer with current experiments, but they are vital for pushing the boundaries of human thought. They remind us that the universe is far stranger, far grander, and far more complex than we can currently comprehend. And that, to me, is the most exciting part. The universe isn't a solved puzzle, it's an ongoing, unfolding mystery, an invitation to forever explore. We, as human beings, are the universe's way of looking back at itself, of trying to understand its own origins and destiny. We are the stardust that became conscious, capable of pondering the very forces that created us and continue to shape our reality. The mysteries of dark matter and dark energy, the before and the why, are not just scientific problems. They are profound philosophical inquiries that challenge our perceptions of existence itself. And this journey of discovery, this relentless pursuit of knowledge, is what makes us truly unique. We live in this precious, vibrant window of cosmic time, a fleeting moment when the universe is just right for us to exist and to ask these impossible questions. The echoes of the invisible are all around us, waiting for us to listen, to observe, to theorize, and perhaps one day to finally understand. The next chapter in the universe's story, and indeed in our own, is still being written. One observation, one experiment, one mind-bending idea at a time. And I, for one, can't wait to see what we discover next. You're still with us, aren't you? After journeying through the birth pangs of the universe, the silent rain of particles, the furnace of creation, and the slow, inexorable pull towards a future of ultimate cold and darkness, we find ourselves standing on the precipice of the unknown. We've peered into the Planck epoch, surfed the waves of cosmic inflation, and watched galaxies bloom like luminous flowers in the cosmic garden. We've even grappled with the invisible architects of reality, dark matter and dark energy, those enigmatic forces that command 95% of the universe's inventory. And yet, as we concluded our last exploration, we recognized that every unanswered question isn't a dead end. It's an invitation, a shimmering, irresistible invitation to further discovery. This is where the true magic of science lies, isn't it? Not in having all the answers, but in the relentless, passionate pursuit of them. It's the thrill of the chase, the intellectual detective work that defines our species. Think about it. We are here, on this pale blue dot, in a precious, vibrant window of cosmic time, capable of asking these profound questions. Your mind, right now, is wrestling with concepts that span billions of light years and incomprehensible eons. That, my friends, is nothing short of miraculous. It means the universe, in some small, beautiful way, is becoming aware of itself through us. So how do we answer these grand cosmic invitations? How do we even begin to chip away at the mysteries of dark matter, dark energy, or the very fabric of space-time before the Big Bang? We rely on a magnificent, ever-evolving toolkit, the scientific method. It's not a rigid dogma. It's a dynamic dance between observation, hypothesis, experimentation, and refinement. It's about listening intently to the universe, deciphering its whispers, and then trying to articulate its story in the language of mathematics and physics. Let's try to picture it. You're a cosmic detective. Your crime scene, the entire universe, your clues, light from distant galaxies, ripples in space-time, the faint afterglow of creation. Your suspects, elusive particles, mysterious fields, warped dimensions. Consider dark matter. We know it's there because we see its gravitational fingerprints everywhere. Galaxies spin too fast to hold themselves together with only visible matter. Light bends around invisible masses in ways that defy our current understanding of gravity. The cosmic web itself, that vast, intricate scaffolding of the universe, was woven predominantly by dark matter. But what is it? Is it made of weakly interacting massive particles, or WIMPs as many hypothesize? These hypothetical particles would be heavy, but interact so weakly with normal matter that billions could pass through your body every second, unnoticed, just like those neutrinos we talked about. To catch a WIMP, scientists have built extraordinary detectors deep underground, shielded from cosmic rays, in places like the Gran Sasso National Laboratory in Italy, or the Sanford Underground Research Facility in South Dakota. Imagine vast tanks of super-chilled liquid xenon, or germanium crystals, waiting in absolute darkness, hoping for the faintest tremor, the most minuscule interaction from a passing dark matter particle. It's like listening for a single raindrop in a hurricane, but the stakes are universe-defining. If we detect one, if we characterize its properties, it would literally rewrite our textbooks and open up an entirely new sector of physics. Or perhaps dark matter is something else entirely, like axions, incredibly light particles that could also interact very weakly, possibly even converting into photons in the presence of strong magnetic fields. Experiments like ADMX, the Axion Dark Matter Experiment, are designed to listen for these faint conversions, turning the vacuum into a giant antenna, hoping to catch the faintest radio signal from this elusive component of our reality. The search is painstaking, expensive, and often yields null results, but every null result is a valuable piece of information, narrowing down the possibilities, pushing us closer to the truth. Then there's dark energy, the even more perplexing entity that's accelerating the universe's expansion. Remember that colossal mismatch between theoretical predictions for vacuum energy and what we actually observe? It's a discrepancy of something like 10 yas now on 1, 20, a number so astronomically large it blows my mind. This isn't just a rounding error, It's the biggest theoretical problem in all of physics, a giant red flag waving in the face of our understanding. To unravel dark energy, we continue to gaze outward, mapping the cosmos with unprecedented precision. Telescopes like the European Space Agency's Euclid mission, launched recently, and NASA's Nancy Grace Roman Space Telescope, set for launch in the mid-2020s, are designed to chart the distribution of galaxies and dark matter across billions of light years. By observing how the universe has expanded over cosmic time, how galaxies cluster, and how light from distant objects is lensed by intervening matter, we can gather more clues about dark energy's nature. Is it truly a cosmological constant, an inherent property of space itself, or is it a dynamic, evolving field, something called, quote, 53, that changes over time? The answer will redefine our understanding of gravity, space, and the ultimate fate of everything. And what about the very beginning, the, quote, fulfissure of the Big Bang, the Planck epoch where our current physics breaks down? This is where the realms of cosmology and quantum mechanics must finally unite, a grand unification that physicists have dreamed of for nearly a century. We need a theory of quantum gravity, string theory, which posits that fundamental particles are not points, but tiny vibrating strings, and loop quantum gravity, which suggests space-time itself is granular, made of discrete loops, are two leading contenders. They offer glimpses into a universe where space and time might not be fundamental, but emergent properties of something deeper. How do you test such mind-bending theories? It's incredibly challenging, as the energies required to probe the Planck scale are far beyond anything we can generate in a laboratory. But cosmologists look for subtle, quote, fissem in the cosmic microwave background, or even in gravitational waves, that might hint at these quantum origins. Imagine the universe itself, through its earliest light and ripples, might be broadcasting echoes of a quantum beginning, waiting for us to develop the instruments and the intellect to decode them. Some even speculate about multiverses, other universes beyond our own, perhaps born from the same quantum foam or existing in higher dimensions. While currently untestable, these ideas push the boundaries of our imagination, forcing us to reconsider the very uniqueness of our cosmic home. The journey into these profound mysteries isn't just about equations and observations, it's about the human spirit. It's about curiosity, about collaboration, about the sheer joy of discovery. It's about generations of scientists building upon each other's work, extending the reach of our collective intellect further and further into the cosmic night. Think of the thousands of brilliant minds, the engineers, the mathematicians, the astronomers, the particle physicists, all contributing to this grand tapestry of understanding. We are the universe's way of contemplating itself, of asking why and how. We are the stardust, animated and organized into complex conscious beings, gazing back at the stardust from which we came. It's a profoundly humbling thought, isn't it? To exist for such a fleeting moment in cosmic time, yet to hold within our minds the capacity to grasp the immensity of billions of years, billions of light years. Every question we answer invariably spawns 10 more, each more intriguing than the last. That's not a failure of science, that's its triumph. It means the wellspring of wonder is inexhaustible. It means the universe will never cease to surprise us, to challenge us, to invite us to learn more. The edge of our knowledge is not a barrier, It's the most exciting place to be. It's where new discoveries are born, where paradigms shift, where the impossible becomes the merely not yet understood. So, as we bring this particular arc of our, quote 58, journey to a close, remember this. The story of how the universe began is not a finished book. It's a living, breathing epic, with chapters still being written, discoveries waiting to be made, and profound insights waiting to be unearthed. We are not just passive observers, we are active participants in this cosmic narrative. Our quest for knowledge is part of the universe's ongoing evolution, and what comes next for us here on, quote, 59. Oh, the cosmos is vast, and its wonders are endless. We'll continue to explore the intricate dance of galaxies, the birth and death of stars, the search for life beyond Earth, and perhaps even delve into the very nature of space and time itself. The universe continues to unfold, and so too will our explorations. Thank you for joining us on this incredible journey through the origins of everything. Keep looking up, keep asking questions, and never stop dreaming about the science that shapes our reality. Your curiosity is the engine of discovery. Until next time, keep those cosmic questions burning bright. What part of the universe's story keeps your mind wandering? Let us know in the comments, and perhaps your question will spark our next adventure. And so, we've journeyed through the cosmic epochs, from the searing furnace of creation to the birth of stars, galaxies, and eventually ourselves. We've seen the universe as a grand unfolding drama, a story written in light and gravity, culminating in the intricate tapestry of life. But as we stand here, gazing out at the vastness, it becomes clear that this story, magnificent as it is far from complete. In fact, some of its most pivotal characters remain shrouded in mystery, whispering their presence through their profound effects, yet refusing to reveal their true forms. We're talking, of course, about the universe's greatest enigmas, dark matter and dark energy. Together, they comprise roughly 95% of everything in the cosmos, yet they are utterly invisible, untouchable, and largely unknown. Imagine walking into a theatre where 95% of the actors are ghosts, silently shaping the plot, moving the scenery, but never speaking a line. That's our universe, and understanding these spectral forces is the next monumental chapter in our cosmic quest. Let's dive first into the silent architect. Dark matter. We've touched upon its role as the gravitational scaffolding, the invisible glue that holds galaxies together, the underlying structure that allowed the cosmic web to form. But what is it? We know it's not made of protons and neutrons, the stuff you, me, and every star are made of. It doesn't interact with light, which is why it's dark. It doesn't absorb, reflect, or emit any electromagnetic radiation. It just is, and it exerts gravity. Think about a galaxy, spinning like a cosmic pinwheel, if it were only made of the visible matter we see, the stars, gas, and dust. It would fly apart. The outer stars would be flung into the void, unable to hold on. Yet, they don't. They orbit far faster than visible matter alone could account for. It's as if there's a massive, unseen halo of material extending far beyond the visible disk, pulling everything together with its immense gravitational weight. This invisible gravitational hand is what we call dark matter. We've seen its fingerprints everywhere, in the rotation curves of galaxies, in the way galaxy clusters bend light from more distant objects. a phenomenon called gravitational lensing, where dark matter acts like a colossal invisible magnifying glass. The most compelling evidence comes from spectacular cosmic collisions like the Bullet Cluster. Imagine two galaxy clusters smashing into each other at millions of miles per hour. The ordinary matter, the hot gas, slows down due to friction, glowing brightly in X-rays. But the dark matter, theorized to be non-interacting, just sails right through, unimpeded. The separation of the glowing gas from the gravitational lensing effect, which traces the dark matter, is a smoking gun, a clear sign that something else is out there, something dark and distinct from the matter we know. So, if it's not normal matter, what could it be? The leading candidates are exotic, hypothetical particles that interact very weakly with ordinary matter, perhaps only through gravity. We're talking about weakly interacting massive particles, or WIMPs, which would be many times heavier than a proton yet incredibly elusive. Or perhaps axions, much lighter particles that could also explain some other cosmic puzzles. There's even the possibility of sterile neutrinos, heavier cousins of the ghostly neutrinos that constantly stream through your body unnoticed. The hunt for dark matter is one of the most thrilling quests in modern physics. Deep underground laboratories, shielded from cosmic rays, house colossal detectors filled with supercooled liquids like xenon. Scientists wait, with bated breath, for the faintest tremor, a tiny flash of light or a whisper of an electron that might signal a WIMP colliding with an atomic nucleus. It's like trying to catch a ghost by feeling for its breath in a hurricane, but with incredible precision and determination. We're also looking for indirect signs, like gamma rays produced if dark matter particles annihilate each other in dense regions of space. And of course, the Large Hadron Collider, that magnificent particle accelerator, continues its attempts to create dark matter particles, if they exist, by smashing protons together at incredible energies. It's a testament to human ingenuity, this relentless pursuit of the invisible. But as profound as the mystery of dark matter is, it pales in comparison to the enigma of dark energy. This is the force that truly blows my mind. The cosmic accelerant, the driver of the universe's ultimate fate. Remember how we learned that gravity pulls everything together? Well, dark energy is doing the exact opposite. It's pushing space apart, not just expanding it, but accelerating that expansion. Imagine stretching a rubber sheet. That's the normal expansion of space. Now imagine that sheet spontaneously starts stretching faster and faster on its own without anyone pulling it harder. That's dark energy at work. Its discovery in the late 1990s was a monumental shock, earning a Nobel Prize and completely upending our understanding of the universe. Astronomers were studying distant Type Ia supernovae, specific types of exploding stars that act as standard candles because they always reach the same peak brightness. By measuring how bright they appear from Earth, we can calculate their distance. The expectation was that the universe's expansion, slowed by gravity, would be decelerating. Distant supernovae should have appeared brighter than expected if the expansion was slowing down. But what they found was precisely the opposite. The distant supernovae were fainter than predicted, meaning they were further away than they should have been if the expansion was slowing. The only way this could be true was if the universe's expansion wasn't slowing down but actually speeding up. It was like dropping a ball and watching it suddenly shoot upwards, faster and faster defying gravity. This inexplicable acceleration is attributed to dark energy, a mysterious entity making up roughly 68% of the universe's total mass energy density. Think about that. Almost 70% of the cosmos is this utterly baffling anti-gravitational force. So what is dark energy? The leading theory is that it's the cosmological constant, a concept first introduced by Einstein and later called his quote 62 before its rediscovery. This idea suggests that dark energy is an intrinsic property of space itself, a constant energy density inherent in the vacuum. As space expands, more vacuum is created, and thus more dark energy appears, maintaining a constant density and driving ever faster expansion. But here's the kicker, and it's a genuine head-scratcher. Quantum field theory predicts that the vacuum of space should be teeming with quota 63, constantly popping in and out of existence, contributing an enormous amount of energy. If this vacuum energy were indeed dark energy, its predicted value is an astounding 10^120 times larger than the observed amount. That's a 1 followed by 120 zeros. This discrepancy, known as the cosmological constant problem, is perhaps the greatest unsolved puzzle in all of physics. It's such a colossal difference that it suggests either our understanding of quantum mechanics is profoundly incomplete, or there's a fundamental mechanism we utterly fail to grasp, perhaps a cosmic cancellation act of unimaginable precision. Another hypothesis is quintessence, a dynamic energy field that changes over time and space, unlike the constant vacuum energy. It's a more speculative idea, but it offers a way around the cosmological constant problem, allowing the dark energy density to evolve. Large-scale cosmic surveys like the Dark Energy Spectroscopic Instrument DESI and upcoming missions like Euclid and the Nancy Grace Roman Space Telescope are meticulously mapping the universe's expansion history and the distribution of galaxies to shed light on dark energy's true nature. Are its effects truly constant, or do they change? The answer will dictate the ultimate fate of our universe, whether it expands forever into a cold, dark oblivion, or meets some other, as yet unimagined end. Now, let's pivot to a mystery that takes us even further back, right to the brink of creation, the before and why of the Big Bang. We've described the Big Bang not as an explosion in space, but an expansion of space itself from an unimaginably hot, dense state. But what was that state? And what came before it? Our current theories of physics, particularly general relativity, break down at that initial singularity. They simply can't describe a point of infinite density and temperature. It's like trying to divide by zero. The equations just scream. This breakdown signals that we need a more fundamental theory, one that unifies general relativity, the physics of the very large, with quantum mechanics, the physics of the very small. This is the holy grail of modern physics, a theory of quantum gravity. Two leading candidates are string theory and loop quantum gravity. String theory proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating one-dimensional strings. Different vibration patterns correspond to different particles. In some versions of string theory, our universe might be just one brain, a higher dimensional membrane floating in a vast, higher dimensional space, potentially colliding with other brains, triggering new big bangs in a cyclic universe model. Imagine a cosmic ocean where our universe is just a single wave, constantly forming, expanding, and then perhaps collapsing to bounce back into a new existence. Loop quantum gravity, on the other hand, suggests that space-time itself isn't smooth and continuous, but rather quantized, made up of tiny, discrete, quote, 68 or quote 69 of space. In this framework, the Big Bang singularity might be replaced by a big bounce, where our universe contracted to a minimum size before rebounding and expanding into what we see today. This would mean there was a quote 70 a previous universe that collapsed, giving birth to ours. These are not just abstract mathematical exercises, they are profound philosophical inquiries. They challenge our very notions of time, space, and existence. Was our universe truly the first? Is it one of many in a vast multiverse, a collection of countless universes, each with its own laws of physics? While currently beyond direct experimental verification, these ideas push the boundaries of human thought, inviting us to contemplate possibilities that are genuinely strange, beautiful, and mind-bending. Finally, let's revisit that tiny yet utterly crucial puzzle we briefly touched upon: baryogenesis. The mechanism behind the universe's matter-antimatter asymmetry. Remember, in the super-hot early universe, matter and antimatter should have been created in equal amounts. When they met, they would annihilate each other in a flash of pure energy. If this had happened perfectly symmetrically, the universe would be nothing but photons and neutrinos, a silent, empty sea of light. No stars, no galaxies, no us. But thankfully, for reasons we still don't fully understand, there was a tiny, minuscule excess of matter over antimatter, perhaps one extra particle of matter for every billion pairs of matter-antimatter. This seemingly insignificant imbalance is why anything exists at all. This is the cosmic lottery ticket that we won, allowing the universe to be populated by atoms, by planets, by life. Physicist Andrei Sakharov laid out the three conditions necessary for this asymmetry to arise. 1. Baryon number violation. Processes where the total number of baryons, protons, neutrons is not conserved. 2. C and CP violation. Violations of charge and charge parity symmetry, meaning that matter and antimatter behave slightly differently, and left-handed and right-handed particles aren't mirror images in their interactions. 3. Out of equilibrium processes. The universe must have been expanding and cooling fast enough that these processes couldn't simply run in reverse and erase the asymmetry. While we have observed some CP violation in particle physics, it's not nearly enough to explain the vast excess of matter we see. Theories abound from coolest electroweak baryogenesis, where the asymmetry is generated during the electroweak phase transition, to leptogenesis, where a fundamental asymmetry in leptons, like neutrinos, is transferred to baryons. Perhaps even more exotic theories involving grand unified theories, guts, or supergravity could hold the key. This puzzle is not just an academic exercise, it's the very foundation of our existence. It asks, why are we here? Why is there something rather than nothing? The answer lies in that almost imperceptible cosmic preference for matter, a preference that allowed the universe to bloom into the intricate, vibrant cosmos we are only now beginning to comprehend. So you see, our journey through the universe's origins has brought us to the edge of what we know, peering into the vast ocean of the unknown. Dark matter, dark energy, the Big Bang's beginning, and the matter-antimatter asymmetry. These are not just footnotes. They are the profound mysteries that beckon us forward. They are the challenges that fuel the next generation of scientists, the questions that keep us building ever more powerful telescopes, ever more sensitive detectors, ever more elegant theories. We live in a truly privileged time, a precious, vibrant window of cosmic time, where we have the tools, the intellect, and the insatiable curiosity to continue unraveling the universe's grandest secrets. The story is far from over. In fact, for humanity, it feels like it's just beginning. We stand, you and I, at the precipice of understanding. We've journeyed through the fiery birth of the cosmos, witnessed the silent dance of dark matter, and grappled with the accelerating enigma of dark energy. We've acknowledged the profound questions that linger, like cosmic whispers at the edge of comprehension, the before the Big Bang, the why of baryogenesis, the very fabric of existence. These aren't just gaps in our knowledge, they are invitations. They're the universe daring us, challenging us to stretch our minds beyond the familiar, to dream in dimensions we can barely conceive. And that, my friends, is where the true magic of dreamy science truly begins. Last time, we touched upon the idea that our conventional physics simply breaks down at the Big Bang's initial singularity. It's like trying to navigate a ship with a compass that only spins wildly when you hit the North Pole. We need new maps, new instruments, new ways of thinking. This is the realm of constant quantum gravity, where the two titans of 20th century physics, general relativity, our blueprint for the very large, for gravity and space-time, and quantum mechanics, our guide to the very small, to particles and forces, must finally unite. They've been estranged for too long, speaking different languages, describing different realities. But to understand the universe at its most fundamental, at its birth, they simply must come together. Imagine trying to describe a symphony using only the physics of a single violin string. You'd miss the brass, the percussion, the harmonious interplay. That's a bit like our current situation. General relativity describes the smooth, curving space-time of planets and galaxies, while quantum mechanics tells us that everything, even space and time, should be jiggling, probabilistic, quantized at incredibly tiny scales. How do you reconcile a smooth, continuous fabric with a jittery, granular reality? This is the grand challenge, the holy grail of theoretical physics, and it leads us down some truly mind-bending rabbit holes. One of the most famous of these rabbit holes is string theory. Now, if you've heard of it, you might picture tiny vibrating strings, and you'd be right. The core idea is elegantly simple, yet profoundly revolutionary. What if the fundamental particles we know, electrons, quarks, photons, aren't point-like dots at all? What if they are in fact incredibly tiny one-dimensional vibrating strings? Think of it like a guitar string. Depending on how it vibrates, it produces different notes. In string theory, different vibrational modes of the fundamental strings manifest as different particles with different properties, different masses, different charges. It's a cosmic symphony, where every particle is a unique melody played on a universal string. And here's the thing that absolutely blows my mind. For string theory to mathematically work, for it to be consistent, our universe can't just have the 4 dimensions we're familiar with, 3 spatial and 1 temporal. Oh no, it requires extra dimensions, Often it's proposed that there are 10 or 11 dimensions in total. Where are these extra dimensions, you ask? Well, the theory suggests they are, quote, 74, curled up so incredibly tightly, so infinitesimally small that we don't perceive them. Imagine a garden hose. From far away it looks like a one-dimensional line, but get up close and you see its second dimension curled around its circumference. In the same way, these extra dimensions might be curled up at the Planck scale, far beyond anything our current instruments can probe. But their existence, even if hidden, could profoundly influence the forces and particles we observe. It's like a secret architecture underlying everything. Then there's GUSSE, loop quantum gravity, LQG, another contender in the quantum gravity arena, which takes a different but equally fascinating approach. Instead of tiny strings, LQG suggests that space-time itself isn't continuous at all, but rather is made up of discrete fundamental loops or atoms of space-time. It quantizes space and time much like energy is quantized in quantum mechanics. Imagine space-time not as a smooth canvas, but as an incredibly fine-grained shimmering tapestry woven from these fundamental loops. At scales smaller than the Planck length, there's no continuous space. There are only these discrete quanta. This perspective offers a tantalizing possibility. If space-time is granular, then the Big Bang singularity, that point of infinite density where our equations break down, might not have been a singularity at all. Instead, it could have been a quote, point where the universe reached a maximum density, and then, instead of collapsing to nothing, rebounded and began to expand. It implies a previous universe, contracting to that point, and then our universe emerging from its ashes, much like a phoenix. The idea of a cyclical universe, an eternal cosmic breath, is genuinely mind-bending, isn't it? Both string theory and loop quantum gravity, in their own unique ways, offer potential pathways to understanding the before and to unifying the forces. They are theoretical frameworks, incredibly complex and still very much under development, but they represent humanity's most ambitious attempts to grasp the ultimate nature of reality. They are our guides into the truly unknown, where the rules we thought we knew might not apply. And from these theoretical forays, particularly from the implications of cosmic inflation and the vastness of quantum possibilities, emerges one of the most provocative and exciting ideas in modern cosmology, the multiverse hypothesis. This isn't just science fiction anymore, it's a serious area of scientific speculation born from the very equations we use to describe our universe. Let's try to picture this together. If inflation, that rapid early expansion, went on forever in some regions, constantly bubbling off new, 70 up. As it expanded, then our universe might just be one bubble in an infinite, ever-expanding foam of other universes. Each of these bubbles could have slightly different physical laws, different fundamental constants, different numbers of dimensions, different histories. This is often called the SEP Level 2 multiverse, or the SEP, 80. This concept tackles one of the most perplexing puzzles we face, the Boole fine-tuning problem. Think about it. The fundamental constants of our universe, the strength of gravity, the mass of an electron, the precise value of dark energy, seem incredibly, impossibly fine-tuned for the existence of life. If they were even slightly different, atoms wouldn't form, stars wouldn't ignite, or the universe would have collapsed back on itself long ago. It's like winning the cosmic lottery an infinite number of times. The multiverse offers a compelling, albeit controversial explanation. If there are an infinite number of universes out there, each with its own set of physical laws and constants, then it's not surprising that we find ourselves in one where life is possible. It's simply a matter of statistical probability. We exist in the universe that can support our existence. This is the essence of the anthropic principle, which comes in two flavors. The weak anthropic principle states that the observed values of all physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist sites where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. Essentially, we observe the universe to be the way it is, because we are here to observe it. It's a selection effect. This strong anthropic principle goes a step further, suggesting that the universe must have properties that allow for the development of intelligent life at some stage. This is where it gets more philosophical and less purely scientific, hinting at a purpose or design, which makes many scientists uncomfortable. But the multiverse isn't just about inflation. There are other flavors, other levels. There's the leveler multiverse, where if space is infinite, then eventually far enough away, there must be other regions identical to ours, simply because there are a finite number of ways particles can arrange themselves within a finite volume. Given infinite space, all possible arrangements must occur somewhere. Imagine a cosmic game of Tetris with an infinite number of blocks. Eventually, the same patterns will repeat. Then there's the Level 3 multiverse, stemming from the many worlds interpretation of quantum mechanics. Every time a quantum event has multiple possible outcomes, the universe splits, creating parallel realities where each outcome occurs. It suggests that every choice you've ever made, every path not taken, exists in a different branch of reality. This is truly the stuff of dreams, or perhaps nightmares, depending on your perspective. And finally, the Can Level 4 multiverse, perhaps the most abstract, where every conceivable mathematical structure corresponds to a real, existing universe. This is where the universe itself becomes a mathematical equation, and every consistent equation describes a reality. It's a universe of pure mathematics. These multiverse concepts are not directly observable, which makes them challenging to test. But they are logical extensions of our most successful theories, and they offer profound insights into questions that might otherwise seem intractable. They force us to reconsider our place in the cosmos, moving from being the sole inhabitants of the universe to potentially one tiny speck in an unimaginably vast ensemble of realities. It's humbling, yet also incredibly empowering, to think that our universe might be just one note in a much grander cosmic chord. This journey into the before and the beyond also forces us to confront the very nature of Time itself. Is time a fundamental river flowing from past to future, or is it an emergent property, an illusion born from the increasing entropy of the universe, much like temperature emerges from the average kinetic energy of molecules? Loop quantum gravity, for instance, suggests that time might not be fundamental, but rather an emergent phenomenon arising from the relationships between quantum atoms of space-time. If time isn't fundamental, what does that mean for the beginning, for the Cestius, quote, 85s, the Big Bang? It could mean that the concept of Gern, quote, 86, simply loses its meaning, much like asking, what is Gerso 87? These are the frontiers where science meets philosophy, where the rigorous pursuit of data collides with the boundless expanse of human imagination. We use our most powerful telescopes to peer back in time, our most sophisticated particle accelerators to probe the smallest constituents of matter, and our most brilliant minds to construct theoretical frameworks that push the boundaries of what we thought possible. We are, in essence, trying to understand the mind of the cosmos itself, to decode the ultimate algorithm that governs existence. And this quest, this insatiable curiosity, is what defines us. It's what makes us these fragile, star-stuffed beings on a pale blue dot, capable of contemplating such profound mysteries. We are the universe's way of looking at itself, of asking its own questions. Our struggle to unify quantum mechanics and general relativity, our exploration of multiverses and the nature of time, these are not just academic exercises. They are the next chapters in the grandest story ever told. They are our attempts to bring light into the deepest cosmic shadows, to find echoes of reality beyond our immediate horizon. So, as we bring this chapter to a close, remember this: the universe is not a solved puzzle. It is an infinite book, and we are only just learning to read its first few sentences. The mysteries we've discussed, dark matter, dark energy, the origin of the Big Bang, the possibility of other universes, they are not dead ends. They are vibrant, living questions beckoning us forward. They are the fuel for the next generation of scientists, the inspiration for new technologies, and the constant reminder that the universe holds wonders far beyond our current grasp. The journey of Flaz just quote, Entras, is far from over. In fact, it's just getting started, and I, for one, can't wait to see what incredible discoveries await us. The universe is calling, and we are listening.